In this video, I'm going to talk about football betting with the multinomial logit, and specifically for this video, I'll be focusing on how to work with three-dimensional arrays in Numpy. So let's get started. We're going to start by restarting the kernel and clearing outputs. All right, so first let's read in our data set. It is the data with football match predicted probabilities that I've talked about in other videos as well. So as you can see, we have all the betting firms and their probabilities for a win, draw, or loss, and the over round applied by that particular bookmaker. And we can also see the team and the enemy team and the eventual goal difference in a match. So here's a draw between KRC Genk and Beerschot AC, and here KSV Circle Brugge lost by 3 points to RSC Anderlecht, and so on. Okay, all right, so in this data set we're going to create our outcome as, call it y, and as you can see, y takes values 0, 1, and 2, with 0 meaning a loss, 1 meaning a draw, and 2 being a win. So we have three outcomes for our discrete variable y, which is why this is an example of a discrete response setting that we have. Y is in 0, 1, or 2. Okay, the conditional probabilities that we'll be computing here for each of the three outcomes are going to take the following form. It's the exponential value of some number given by an inner product between a vector of covariates and a vector of parameters. And as you can see, so that we're going to have different vectors for the different outcomes of coefficients. We're going to have theta j for each outcome j, and j equals 0, 1, or 2, and we're going to have a vector of coefficients possibly varying both over individuals and over outcomes. And that'll make sense in a second. And for normalization, we're basically going to have to assume that one of our outcomes has coefficients normalized to zeros, or equivalently, that one of these utility indices, x theta, is equal to 0 for one of the j's. And we're going to just pick the first one, j equals 0 in Python base 0 indexing. All right. Okay, so you can read all this on your own. Here, let's set up the data set and let's create a home dummy both for the win utility equation, if you will, and the draw. And similarly, for win and draw, let's create a constant that is equal to 0 for everyone. And what I'm doing here is I'm also ensuring that, the home dummy that applies to that is going to apply to the win equation is 1.0s, whereas the home dummy itself was true or false, and that's just because NumPy works better with floats or at least integers. All right, let's work with a small scale model here, implying that the chosen columns are just these columns that I'm writing up with a list comprehension with a double loop, but it's basically just a lazy way of writing these 6 variables without, I think, or 6 variables, yeah, without possibly I've even spent more characters, but yeah, these comprehensions are cool. Okay, and then let's delete all of the observations that have missings in any of these variables. So we're only keeping 87% of our original sample, just to not deal with missing values. Okay, so here's the crux of this video. We want to convert our data frame from pandas to NumPy. And how do we do that? Well, that didn't work. Okay, so what we basically have to do is we have to, whenever we want to extract a variable like our outcome y, well, we just hit .values, and that gives us access to the underlying Numpy array that's lying behind the pandas data frame, which is kind of just an interface to the underlying Numpy arrays with added functionality. So we want to access those Numpy arrays, and for our y variable, we want to make sure that it's not a one-dimensional vector, we want a two-dimensional vector. So we're going to use our reshape -1, or n, 1 as it's going to be, but we haven't created n yet. That's created in this cell. Here we go. So that's our outcome, and then our x variable, we're gonna pull out those columns here. X, it's that of cols, and just to remind ourselves, the columns that we're looking for are these 6 variables: the draw probability and win probability, and we want them to enter the utility for draw and the utility for win respectively, and we have a dummy for home affecting the draw utility and a home affecting the win utility, if you will. So if we just pipe out these values here as the Numpy underlying Numpy matrix, we get an n/6 matrix. But really we would like to think of it as not 6 explanatory variables. We could think of it like that and allow the draw probability and the win probability to affect the draw v index, the draw probability, and have the draw the draw probability and win probability affecting the win outcome. But we just want 3 covariates explaining each of the entering in each of these utility indices here, in each of these x's. So 3 in this x, and 3 for j = 1, and 3 in the x for j = 2. So how do we do that? Well, basically, if we take this matrix first and just create it and call it x, then what we want is we want x of all of the rows, and then we want columns 0, not 1 but 2, and not 3 but 4. Here we go. These are the ones, the explanatory variables we want for the draw outcome, and the corresponding ones that we want for the win outcome are these. For these particular rows, they happen to be, well, no, as you can see, the probabilities here are different, right? Because here we have draw probabilities, and here we have win probabilities. They tend to be higher for some of them, although for this one, it happens to actually be, looks like it's identical, so they probably have flat odds there. But you can see, of course, whether it's a home match or not is the same here. So that for that variable, that particular variable, the home dummy, is identical. Of course, that's how we created that variable here. It's just a copy of the home dummy. So those two are identical in the 2 arrays. But instead of keeping track of, what we could do is we could have created an x1 array and an x2 array. We could have done that and then started multiplying them by parameter vectors. So we could say x1 times, and we could have 0.1, 0.1, 0.1 as our theta parameters affecting the first. Probably this one needs to be primed. So we could have done this. Just this would have been our utilities for the first outcome, or rather that would be the draw outcome. So this would be utility for draw, and a similar one for our second. And this is if the 2 parameter vectors theta, let's create theta as a vector of 1s, and we want it to be k tall and j minus 1 across. So theta naught is like this. So we have parameters for the utility of the j = 1 alternative and j = 2, but not for j = 0, because for those utilities, the thetas are normalized to zeros. So in that case, what we're doing here is we're multiplying it by the first column of theta naught, and here by the second column of theta naught. That's one way of doing it. And now we have our utility 1 and we have our utility 2, and both of these are n vectors. So this would be one way of computing choice probabilities. Then all we would need is to say that the normalized alternative is just a vector of zeros. And then we would be able to compute our choice probabilities by going probs equal to p.exp. Well, I guess we should do probability for, let's take the probability for the outcome 1. That's the utility of 1 divided by exponential value of u0 plus np.exp of u1 plus np.exp of u2. This would give us a vector of choice probabilities for the first outcome, and we could do the same thing with outcome 0. That's just a matter of what we have in the numerator, right? So if we revisit the choice probability formula up here, you can see that it's the exponential value of the x theta for outcome j, if that's the choice probability we're after. So we can ask, what is the choice probability of observing y being equal to 1? Well, then we take the utility index corresponding to the x theta for j equals 1. So this would be one way of computing the choice probabilities. Props 0, props 1, and props 2. But we want to do it a little bit smarter than this and without having to hard code these choice probabilities. And one way of doing that is by working with three-dimensional arrays. Okay, so how does it work with three-dimensional arrays? Well, what if we just, instead of doing this, we take our x that's coming out of data values and we reshape it to be an n by k by j minus 1 array. What does that mean? Well, as you recall, this is 45,000 by 6. So that's also what this underlying matrix is. So we can reshape it to be n by k by j minus 1. All right, now we have a big three-dimensional array, and this is what is in x after we run this cell. And if we pick I equals 0, all of the k's and all of the j's, we're getting a 3 by 2 matrix out. And if we pick these individuals, the first individual, the second individual, and the 10 to last individual, then here's what we're getting out. Index 0, 1, and actually I think that this is the wrong row because we didn't drop the nans here yet. Did we? Oh, we did. Good. Anyway. Right, it's keeping, okay, yeah, so what's confusing me is that this index number is larger than the number of rows in dat, but that's because we haven't reset the index value, so this index is actually referring to the position in the original dat data frame before we dropped observations, so that we can actually re-find this row in our original data set should we ever want to. Anyways, here are the matches, and let's also find the enemy team here. Okay, so the first one was KFC Genk versus Beershot, and the last one is SD Eibar versus FC Barcelona. You can see the probability assigned by the bookmakers that SD Eibar wins over Barcelona is just incredibly small probabilities, very long odds. So these are the first 3 rows, and this is what X looks like. We've taken out the first 3 rows from the big matrix X, or for the first 3 sets, and as you can see, it's what we have is basically we have 3 matrices, each of them 3 by 2. Right? So we have 3 matrices, each of them are 3 by 2. And that's a 3-dimensional array. And let's now start thinking about how we can do algebra or do computations with such a 3-dimensional array. All right. So theta, our parameters is we have 1 theta for alternative 1 and 1 theta for alternative 2. And we don't have a theta for alternative 0 because that's normalized to zeros. So we're not keeping track of that big fat 0. The reason why we're not doing that, we could have expanded theta and just said, let's just stack some zeros in front of theta. Like this. Oops. Oops, not n. Of course, k. We could have kept track of this, but that would have confused our optimizer later because it would think that these would also be values that we'd be changing, whereas actually we'll only be optimizing over these thetas. These are the only ones that we'll be searching over when we eventually get to estimation. And if we want to think about what the labels are for these columns, then, well, this theta corresponds to the bet 365 probability assigned to a draw. This is the coefficient on the home dummy as it affects the index, the probability for a draw. And this is the constant affecting the draw outcome. So if we wanted, we could add that the columns correspond to draw and win, respectively. Whoops, columns. So these are our 6 parameters. All right, let's now learn multiplication by starting out simply with a 1-dimensional array. So if we just pick out I equals 2, so 2, that's the last element of x, because as recall, x has 3 elements. So first one is this, second one is this, and the third and last one is x of 2. So that's what it looks like. And as you can imagine, we can multiply that by our matrix theta, and this is just our guess of thetas, which is 0.1 everywhere. And when we do that, here's what we get back. We get our x values, but shifted 1 decimal point to the right, of course, because we're just multiplying it by 0.1. Okay, so now we want to create the utility index x theta. You can see I'm using betas here, but that really doesn't make a difference. But let's change it to theta just to be consistent with our own notation here. So this utility index is basically we're taking the product of, we want to take the product, the element-wise product, and then we want to sum over k. And remember that this is k by j minus 1. So k is equal to 3, and we have 3 rows here. We can do that by summing over the 0th axis in this 2-dimensional array. And what we can see is that 0.1 plus 0.009 is giving us close to 0.11. That makes sense. And this is 0.104, and that's what it says here. So that's the sum over the k's here. And there are 2 numbers here because we have a utility value, a utility index for the 2 outcomes j equals 1 and 2. And then we just have to add our 0th alternative, j equals 0, the normalized alternative, which has utility value of 0. And how do we put a 0 value in front of this vector? We do it by horizontally stacking 0 in front of this whole thing, which is written out here. You could also say xb sum is equal to this, and then down here we're putting a 0 next to our xb sum. And now we're pretty much good to go, because now we have the utilities for the 3 alternatives. So as you recall, the choice probability formula, you can also scale down, is given by the exponential value of the v divided by the sum of the exponential values of all of the v's. Those are the logit choice probabilities. So we basically just have to say, what is the exponential value of u? That's what goes in the on the top of the fraction in the numerator, and in the denominator we want the sum of this. And here we don't have to specify an axis because it's a one-dimensional array. So the sum of those exponential values, it's 1 plus 1.1, that's 2.1, and then plus 1.1, that's 3.2 approximately. There we go. So this is what's going to be in our denominator. And then our choice probabilities is that we take this denominator here, which is just a float, just a number, and then our vector of exponentiated utilities, so exponential value of 0 is 1, and so on. We just divide that vector by this number everywhere, and then we get our choice probabilities. And we can already see that the sum of the choice probabilities is 100%, up to a tiny, tiny, tiny round-off error. Very good. So this was working with the two-dimensional, or with just one of those elements, and now let's work with the full array. So as you can see, when we have x here, what we want is we want to take our theta, which is our 3×2 matrix of parameters, and we want it to be multiplied to this matrix, and to this matrix, and to this matrix. And then we want to take the sum of this row with this row with this row. And we want to take the sum of this row with this row with this row after they've been multiplied. So we want to first multiply x by theta. And this is pretty neat, because what's happening behind the hood, if I just write x times theta, is that Numpy is realizing that x, and theta, they don't have the same shapes. So how does it deal with the multiplication of these two things? And this is always tricky when you're working with multidimensional arrays. And what it's doing is it's realizing, hey, these dimensions actually match. So I'm probably supposed to just multiply this small array to each of these 45,000 3×2 arrays. Remember that x, or x matrix, or in the case of the smaller one with 3, it just multiplies the theta to each of these 3 smaller arrays. And it's actually the same as taking our theta and writing np.tile. So you tile and repeat theta 3 times in the first dimension, 1 time and 1 time. That gives us theta repeated down many times. If we take this and multiply that with x, now the two arrays have exactly identical size. And we can see that this is actually what it's doing. It's just repeating theta many times down. But you always have to be wary when this is writing it like this, x times theta. They don't have the same dimensions, and relying on Numpy interpreting correctly how to repeat theta can always be dangerous. Similarly, if you wanted to use the add operator, so the difference between a multiplication with times and add is that when you use add, matrix multiplication, you're implying that you want some kind of sum to be performed. As well. Plus you also then typically have to write some a proper transpose. But in this particular case, it turns out that it's not really doing what we want to. Alright, but now what we have, this array that's coming out here doesn't have the final dimensions that we want because its shape is 3×3×2, but we want to sum over k. That's what we're trying to do here. We're summing over k of x ijk times theta jk. So what we do is we just type sum axis equals 1. So it's not axis 0 and it's not axis 2, it's axis 1 that we want the sum to be done over. And the resulting array from this should be n by j minus 1, or it will be n by j minus 1. And we can see here, let's confirm it, 0.009 plus 0 plus 0.1, that's 0.109, and that's what it says here. So it's doing it in the correct manner. This number here is the sum of that one, and that one. So that's how it's doing the summing of this three-dimensional array. And let's now finally scale it up to the full size of the data set. So it's just a matter of noting that it didn't really make it. This time we have a first dimension of 45,000, and we still have our theta is just 3 by 2. And then it turns out that, of course, Numpy interprets this correctly and repeats our theta matrix every time. So if we can print the two and compare them, it's multiplying this number by 0.1, so we're shifting the decimal place, right? And again, it's just a question of summing over the middle axis, axis 1, and then what we're getting out as a result of this operation is an n by j minus 1 array. Great. Great. So x beta, that's when we've summed over these products here. It's just this item up here. And now we can add the 0 in front. This is our vector of zeros. And now we have our full matrix of utilities, which is now finally not just n by j minus 1, but n by j. We've added the normalized 0 column. And then again, in just the same way as before, we can compute the choice probabilities by computing the exponential values. Let's actually do this in 2 steps. First, we compute the denominator, which is we take the exponentiated values of our utilities, and then we take the sum over axis equals 1, because we want the axis, we want to take the horizontal sum. Here we go. There's an n array coming out of that, but we want it to be a two-dimensional array, a two-dimensional vector, so that it's standing up in this way, because when we do it like that, if we subtract it from another n by j matrix, it does so correctly. But if we don't have this reshape on, we can see that it's giving us this error that operands could not be broadcast together. And we can see that it's pretty clear what it should be doing, because they have the same dimension along this line, but Python is refusing to do it because there's not a second dimension to this array. So that's why we're doing the reshaping all the time. And this, by the way, is the same as going -1, 1, but here I'm just telling it explicitly. I'm just showing you that I know what the first dimension is going to be. And we can see that if I press K, then it's going to complain, because of course that's the wrong number of lines. So being explicit about the number of observations that you're expecting is good in good code practice, because it means that you'll get an error if something unexpected is happening. All right, so this is our full vector of choice probabilities, and as you can see, they're nice and beautiful between 0 and 1, and if we sum over the second axis, we're getting that they sum to 100%. So that was fortunate. Oops. So that's how we compute choice probabilities from a three-dimensional array.